Everyone, in this video I'd like to expand on our knowledge of the derivative and how it will apply to the study of kinematics and motion graphs. Our introduction to the derivative just dealt with the normal y and x axes, where those axes didn't tend to represent anything in particular, but in kinematics you know that those, and motion graphs, you know that those axes represent things in physical reality that we can actually measure and do calculations with and things like that. We will start by applying our knowledge of the derivative to uniformly accelerated motion. I will consider just one dimension at this point, one dimension in the x direction. The x direction will be down the ramp. Down the ramp will be considered the positive x direction. And so I'm going to use logger_pro to generate both a position versus time and a velocity versus time graph for this motion. You should be very familiar with this motion as of now. But then now we're going to actually throw some derivative, some calculus at it. Okay, so here we go. We got our velocity versus time graph on the bottom and our position versus time graph at the top. For uniformly accelerated motion, we always have a position time graph that is quadratic or parabolic, and our velocity versus time graph will always be linear. And then we can go from here to our acceleration versus time graph. Because it's uniformly accelerated motion, our acceleration versus time graph will be constant. It'll just be a horizontal line, zero slope. But let's focus on position versus time graph first. And what I'm going to do here is actually use logger_pro to find the equation for this graph. And to do that, we just do a curve fit. And I know it should be parabolic, so I will choose a quadratic. And I get this box. You can't see it on the video, but that box I can actually write the equation. So if you remember from last year, we have at the top it says x equals, and I like writing x as a function of time, right? In math class we write our y coordinates as functions of the x-axis, our independent variable. So now we have our position in the x direction as a function of time will equal, and what I got here is 0.1849 t squared plus 0.09426 t, and then plus 0.2242. So that is our equation for this particular parabola. When you do problems, you're not going to have all these decimals, but because this is the actual motion of an actual object, that we have pretty sophisticated programs and devices to actually take the measurements and produce the data. We do have a lot of decimals to deal with, but the same physics will be here. Now, we should know that on a position versus time graph, the slope is the velocity. And since the slope is the derivative, we know that the derivative, dx dt, or the derivative of our position function x of t with respect to t, will be the velocity. So if I take the derivative of my position function, I should get the equation for our velocity time graph. So let's go ahead and do this derivative real quick. So I'm going to say x prime of t. Right, that's one way of denoting the derivative. We've seen several so far, and I have that you can use whichever one you want. So that's going to equal, remember our power rule, we're going to take the exponent, bring it down into the front. So 2 times 0.1849 times t, well, let me put the t in here, times t to the 2 minus 1 power. So that's just going to be t to the first power. Yes, you can leave off that 1. You can leave off the first power because t to the first power is just t. And then we do, using our sum and difference rule, we'll just do the derivative of the next term in the equation. So this is technically t to the 1 power, so I bring the 1 down in front, times the coefficient here, that's the constant multiple rule, times 0.09426, times t to the 0 power. T to the 0 power, we all know, is just 1. It doesn't matter what number t represents. It could be a billion seconds, it could be 1 millisecond, but that number to the 0 power is always just 1. And then the derivative of any constant, you should have realized that after you've used the limit definition to do some derivatives, or just done the derivatives on that formula, or on the last worksheet, you should know that the derivative of any constant is always 0. So keep that in mind, because technically this is times t to the 0 power. So when I apply the power rule, the 0 comes out in front and this whole term goes away. And so let me just simplify this. We have the derivative x prime of t is going to be equal to, I should have had my calculator out here, but I forgot. Ignore the ringing phone. So 2 times 0.1849. That's going to be 0.3698 t plus, this is now a constant. So t to the 0 power again is just 1, so it's just going to be plus 0.09426. So, and this is the derivative of our position function, which tells us the slope of the position function at any t value. And that slope will tell us the velocity of the object at any value for t. And so I can also say that the derivative of my position function is my velocity as a function of time. And again, that is 0.3698 t plus 0.09426. So what that means is that if I pull up the logger pro graphs, the position versus time and velocity versus time graph, if I look at that velocity versus time graph and I find the equation for it, I should have an equation that won't match this exactly, because this is real world data, using real world data, which tends to be a little messy, but it should be pretty close to that. And so let's actually see if that's the case. So let me go down here. I'll try to get that same range of data, and then I do a linear fit, and I get the following equation. I'll write it over here. So now I'm on my velocity versus time graph, so I have velocity as a function of time will be equal to, and what do I get? I got my slope, 0.36, oh, that's hard to read. 3680 t, maybe I need some glasses, plus 0.09553. Plus 0.09553. So that's my velocity versus time graph as read from my velocity as a function of time equation as read from my velocity versus time graph. And again, it's not going to be exactly, but it's pretty close. There I got 0.3698 t. Over here I got 0.3680 t. That's almost exactly the same. And my intercept 0.09553, or my constant value 0.09426. So that's pretty close too. And for our intents and purposes in this class, those are pretty much the same. So that's how we can use the derivative on a position function to determine the velocity function. And then if I have constant acceleration, meaning my velocity versus time graph is linear, that means my acceleration should be a constant. You know, this is uniformly accelerated motion. That means that the acceleration should not change. And so if I was actually to plot an acceleration versus time graph, Logger Pro is not very good at plotting acceleration versus time graphs, so I'm just going to draw it here. But my acceleration should be the derivative of my velocity function, right? The slope on my velocity function tells me the acceleration. And so if I do the derivative of my velocity function, v prime of t, that's actually going to be my acceleration function as a function of time. And once you do a few derivatives of linear functions, they're pretty easy, because the t has a 1 coefficient. The 1 comes down into the front, multiplied by the coefficient in front of the t, times t to the 0 power, which is just 1, which a shortcut is just 0.3680 t. And then the derivative of the constant value is just 0. So now I can get my acceleration. Oh, not t, I'm sorry, that t doesn't go there. Technically it's t to the 0 power because I subtract 1 from the exponent, but t to the 0 power is just 1. And so my acceleration is what I expect. It is a constant number. And so if I was to plot that on my acceleration versus time graph, it would be a horizontal line, and the y-intercept would be at that value, 0.3680 0.668 if we're in meters per second squared for our acceleration value. Okay, so that's a little introduction to a uniformly accelerated motion, but using the derivative. In the next video, we'll actually start talking about non-constant acceleration, which we couldn't do in AP Physics 1 or pre-AP Physics because we can't deal with non-constant accelerations without the derivative. Okay, all right, that's about it for this one.